Good morning, everyone. I am Sunil Kumar Vishwakarma, working as an assistant professor in the Department of Computer Science, School of Engineering, BBD University, Lucknow. Today, in this lecture, I am going to discuss the topic error control, why it is named error control. I will tell you in this lecture, and what are the functions. Error control in data link layer is the process of detecting and correcting data frames that have been corrupted or lost during transmission. Because error is not avoidable. When there is need of transferring data in the network, there are chances of errors. Means that signal can be affected by any noise source or any interference. So after that, we say that this message is in error, this signal is in error. Okay. In case of lost or corrupted frames, the receiver does not receive the correct data frame and sender is ignorant about the loss. So data link layer follows a technique to detect transit errors and take necessary actions, which is retransmission of frames whenever error is detected or frame is lost. The process is called automatic repeat request. Now, error control techniques. Error control involves both error detection and error correction. It is necessary because errors are inevitable. Inevitable means unavoidable in the data communication. Because in spite of the use of better equipment, we are using better equipments comparatively and reliable transmission media based on the current technology. In spite of these things, errors are very common in the data communication. So, when an error is detected, the receiver can have the specific frame retransmitted by the sender, and this process is known as automatic repeat request. For example, internet's unreliable delivery model allows packets to be discarded if network resources are not available and demands the automatic repeat request protocols make provisions for retransmission. So in error control, there are two techniques, error detection and error correction. First, we will see the error detection techniques. If error will be detected in the signal or in the data, it will be corrected also. Okay. Now, errors. There are three types of errors: single bit errors, multi-bit errors, and bust errors. There are some basic differences among these three types of errors. We will see one by one. First is single bit error. Here it is shown, data is shown in the form of digital form. There are 8-bit data 00000010, and transmitter or sender sends it to the receiver. This data is sent and it travels through some communication medium. It may be wired or wireless, and after that it is received by the receiver. But during transmission, due to some noise source or anything else, 5th bit of the data is changed from 0 to 1. Okay, it is shown in the figure to this yellow color. So if only one bit is changed during the transmission, this type of error is known as single bit error. Okay. Now, multiple bit errors. In multiple bit errors, again some data is transmitted, sent, and some data is received. Here we can see that there are two digits that has been changed. The second bit from left to right, that is 1, it's changed to the 0. 1 is sent and 0 is received. And the fifth bit, 0 is sent, and in spite of 0, it is changed to 1 and 1 is received. So if there are two digits which are changed during the transmission and they are not contiguous, not continuous, this type of error is known as multiple bit error. Now the third category of error is burst error. In burst error, there are too many bits are changed from when data is transferred from sender to receiver. Here we can see that starting from 4th bit, from 4th to 8th bit, all the bits are changed at the receiver end. 0 is converted to 1, next 0 is also converted to 1, 1 is 0, 0 to 1, and 0 to 1. So, and these bits which are changed, these are in the continuous sequence. So this type of error is known as burst error. Okay. Now, redundancy. What is redundancy? What are the redundant bits? Why it is added? Why these bits are added with the data? So here, sender and receiver is shown, and there is communication channel between the sender and receiver. Some data, for example, 101 000000000100101. This data is input to the generating function, and generating function generates some random bits. Here it is 101101, and these generated bits are known as redundant bits. What is the use of these redundant bits? These redundant bits or extra bits are added with the data, and along with data these bits are transmitted to the receiver. At the receiver end, again with this help of checking function, it checks, and with the help of redundant bits, it takes the decision whether the data has to be accepted or rejected. Okay, so here in this diagram, it is shown that data is input to the generating function, and after that some redundant bits are generated, and after generation, data and that redundant bits along with transmitted through the communication channel, and at the receiver end with the help of checking function, it is checked that data will be accepted or rejected. So finding redundant bits and adding with the data, this whole process is known as redundancy. Okay. So now, because error correction is involves two techniques, error detection and error correction. So first we will see error detection techniques, how errors will be detected. So for that, there are four techniques for error detection. First one is simple parity check. Second one is two-dimensional parity check. Third is checksum. And the fourth is cyclic redundancy check. These are four popular techniques for the error detection techniques. Now we will see one by one what are the functions and how it works, how it detects the error at the receiver end. First is simple parity check, and another name is one-dimensional parity check. So simple parity check is the most common and the least expensive mechanism for error detection, and it is known as, and this is the reason it is known as simple parity check. In this technique, a redundant bit, I have already told you some extra bits. Here a redundant bit is called parity bit, is appended to every data unit so that the number of ones in the data unit after including this parity bit becomes even. Means the number of ones in the data including parity bit must be even, because here we are talking about the even parity. So blocks of data from the source are subjected to check bit or parity bit generator form. When a parity of 1 is added to the block, if it contains an odd number of ones, so if in the data there are a number of ones in the odd number, then a one extra one is added so that the total number of ones will be even. And if 0 is added, if it contains an even number of ones already. So at the receiver end, the parity bit is computed from the received data bits and compared with the received parity bit. So this scheme makes the total number of ones even. That is why it is called even parity checking. Now we will see 4-bit word, different combinations of the data words and the corresponding code words. Okay. So these data represents the possible 4-bit data words and corresponding code words. Possible 4-bit data words and its corresponding code words. So here in the first column, this is decimal values from 0 to 15, and corresponding every value, corresponding 0, there is a data block for 4 bits, 4 zeros, and that 1 is represented in the binary 0001. It is assumed that you know that how these values are converted in the binary 4-bit binary sequence. Okay. And after 1, 2 is converted in the 4-bit data block 0010, and 3 is converted 0011. This is very simple, and in this way you can convert this data from 0 to 15 in the 4-bit blocks. And after that, in the third column, there are some bits added. In the first row, decimal value is 0 and the data block contains 4 zeros. And here, when we talk about the number of ones in the data block, in the first row, there are no number of ones, 0. So parity bit will be 0. And using this parity bit, code word will be 5 zeros, 0, 0, 0, 0, 0. But when we talk about the second row, 1 is represented as a 0, 0, 0, 1. In this data block, the total number of ones is 1, that is odd, and we have to make it even. So if there are number of ones, how many number of ones? 1. So we will add 1, extra 1 as a parity bit for making the total number of ones even in the data. So 1 is added as a parity bit and the code word is 00011. That 1 is appended after the data in the code word. Or we can say that parity bit is appended for making the code words. So in this way, these 16 different code words are generated for this given decimal values 0 to 15. Okay. So this is the concept of even parity checking scheme. With the help of this flow chart, you can say, this diagram, you can understand the concept of even parity checking scheme. There are two ends, sender end and the receiver end. At the sender end, there is data 1011011. That data is input and the compute parity bit, and after that parity bit is computed. How many ones are there in the data? Here 5 ones, and 5 ones are odd number and we have to make it even. So for making it even, we have to add 1 as a parity bit. 1 is added and 1 is appended. So this is the data word. And after that, it is transmitted through the transmission media. At the receiver end, this data is received, and with the help of this data, again parity bit is computed. If after computing, if it gives the result even, if yes, even, then receiver accept the data. If it is odd, it rejects the data. So this is the simple logic of even parity checking scheme. Note that for the sake of simplicity, we are discussing here the even parity checking. We can also check odd parity checking, but here we have assumed that the even parity checking, where the number of ones should be an even number. It is also possible to use odd parity checking, where the number of ones should be odd. Okay. Now the performance. An observation of the table reveals that to move from one code word to another, at least 2 data bits should be changed. Hence, these set of code words are said to have a minimum distance, or we can say this is the Hamming distance of 2, which means that a receiver that has knowledge of the code word set can detect all single bit errors in each code word. So after discussing this simple parity check, we can say simple parity check can detect all single bit errors in the each code word. And what is code word? Code word is the data plus that parity bit. However, if 2 errors occur in the data word, it becomes another valid member of the set, and the decoder will see only another valid code word and know nothing of the error. Thus, errors in more than one bit cannot be detected. In fact, it can be shown that a single parity check code can detect only odd number of errors in a code word. So this is the performance of the simple parity check. Now, two-dimensional parity check. So performance can be improved by using two-dimensional parity check, because in previous technique we have used one-dimensional parity check. Here we are using two-dimensional parity check, which organizes the blocks of bits in the form of table. Parity check bits are calculated for each row, which is equivalent to a simple parity check bit, and parity check bits are also calculated for all the columns. Means if we are using two-dimensional parity check, in two dimension there are rows and there will be rows and columns. So simple parity check will be used for each row and for each column also, and these parity bits are sent along with the data. At the receiving end, these are compared with the parity bits calculated on the receiver end. Okay, now we will see the logic, how it works with the help of example. So this is the two-dimensional parity checking. Original data is shown. There are 4 data words. First is 10110011, and after that 10101011. Third is 010111010, and the last is 11010101. So when we have to apply the two-dimensional parity checking, we arrange this data one after another. Okay, so below the original data, the data is arranged, and we can see this data in the form of row and the form of column. When we talk about the first row, here it is written 10110011. If we want to count the number of ones in this data, there are 5 number of ones. So if there are 5 number of ones, this is odd, so we have to make it even. So for this we have to add 1 as a parity bit. So first, in the first row, last value is 1 as a parity bit added. In the second row, 10101011, here again the number of ones is 5, so we have to add 1 as a parity bit for making the even parity. In the third row, the number of ones is 4, so for this 0 is added as a parity bit. In the fourth row, 11010101, the number of ones is 5, so 1 is added as a parity bit for making it 6 even. So in this way row parities are calculated. With the help of this data, again we have to calculate column parities also, because it is two-dimensional parity checking. When we see first column, there is 1101. The number of ones in the first column is 3, so 1 is added for making it 4 or even. In the second column, 0011, number of ones is 2, that is already even, so we have to add 0. In this way, for all the columns, parity bit is also calculated. The parity bit which is added for the row parities, for this also column parity will be calculated. So number of ones in the last column is 3, so 3 is odd, so for this extra 1 is added in the last column as a parity bit. So these are row parities and column parities are calculated when the time in at the time of data sending of data. These code words row wise it's sent to the receiver. Okay, so in the data to be sent, what is written here? The first row value 101100111 triple one, and after that it is separated by second row 101011011 again 1. So how many data words, code words are there? 1, 2, 3, 4, 5. This data is sent to the receiver in this way. Of the performance. Two-dimensional parity checking increases the likelihood of detecting bust errors. As we have seen that a two-dimensional parity check of n bits can detect a bust error of n bits. So bust errors can also be detected with the help of two-dimensional parity check. A bust error of more than n bits is also detected by 2D parity check with a high probability. There is, however, one pattern of error that remains elusive. If 2 bits in one data unit are damaged and 2 bits in exactly same position in another data unit are also damaged, the two-dimensional parity checker will not detect an error. So this is the problem with the two-dimensional parity check. For example, if two data units 11001100 and 10101100, a first and second from last bit in each of them is changed, making the data units making the data units 01 00 110 and 00 10 triple 10. The error cannot be detected by two-dimensional parity check here. So this is the problem with the two-dimensional parity check. Now this problem will be removed in the next technique, that is checksum. Checksum is the third error detection technique. How it works? In checksum error detection scheme, the data is divided into k segments, each of m bits. So in this senders and the segments are added using 1's complement arithmetic to get the sum, and this sum is complemented to get the checksum. So there are two techniques are used. The checksum segment is sent along with the data, and at the receiver's end all the received segments are added using 1's complement arithmetic to get the sum. Again the sum is complemented. If the result is 0, the received data is accepted, otherwise discarded. So after this we will see with the help of example how it works. Here it is shown sender's end for the calculation of the checksum, and after that receiving end for the checking of the checksum. In the figure A, here k is equals to 4 means there are 4 segments, and m is equals to 8 means how many bits are there in the each data segment. So first data segment is 10110011, and after that second data segment 10101011. This is assumed, for example. So first two data words are added with the ones complement. So if we see from right to left, 110, after that 11 and 1 carry, which is 1, and after that 00 1 1. So in this way this calculation is performed with the help of ones complement arithmetic. After the addition, one carry bit is generated, and this one again is added with the data, again is added with the result which was generated by adding first two data bits, two data words. And after that, whatever the result is received as a 0 1 0 5 ones, after this third data word is added, that is 0 1 0 1 1 0 1 0, and after the result fourth data word is added, and finally it is found that as a sum 10004 ones. So this is the sum. But how it works in the procedure, it is given that all the data are added using ones complement, and finally checksum is calculated after complementing that data. So sum is complemented, 10004 ones is converted to the 0 zeros. So sum is found and the checksum is found. So when we talk about the transmission of data, that four data words along with this checksum is transferred at the receiver end. Receiver end receives the data, and at this time receiver receives how many code words? 5, because 4 is the data word and fifth one is the checksum calculated is also sent. The same way all the calculations are done, and in the last we found the sum all ones, and after that complement is found. If there are all zeros in the complement, data is accepted. If there is any single one in the complement, data will be rejected. This is the beauty of the checksum technique for the error detection. Okay. Now the performance. Two-dimensional parity checking increases the likelihood of detecting bust errors. A two-dimensional parity check of n bits can detect a bust error of n bits. A bust error of more than n bits is also detected by two-dimensional parity check with a high probability. So there is, however, one pattern of error that remains elusive. If 2 bits in one data units are damaged, okay, the two-dimensional parity check will not detect an error. So the problem which was detected by the two-dimensional parity check, and that was removed in the checksum technique. So we have discussed in this lecture 3 error detection techniques, and in the next lecture we will discuss the 4th detection technique, that is cyclic redundancy check. Thank you.